I'm Josh Sachs. I work at Invincia, and I direct a data science group there. So we've been doing a lot of different machine learning projects over the years. And so the first part of the talk, so this talk is about those projects and some sort of general observations that I've had over the years working on security data science. The first part of the talk was sort of a general overview of data science, and then a discussion of particular issues that come up when you apply data science to security and how we can address those issues. This part of the talk is going to be a deeper discussion of 3 different projects that we've done in my group. So I'm going to talk about methods and results, and it's going to be a bit more technical. Okay. Okay. So the first talk I'm going to talk about is this deep neural network-based malware detection project that Konstantin Berlin and I have done over the last few months. So I'm going to talk about the method that we developed, and I'm going to talk about an evaluation that we did on about 500,000 binaries, and an evaluation we did against actual customer data. Then I'm going to spend a shorter amount of time talking about work that Giacomo Bergamo and I did on basically given our knowledge of a given malware family, let's say like Zeus or Citadel, can we forecast into the future how popular that malware family will be? So we developed a model for doing that I'm going to talk about. And then finally I'm going to give a demo of a system that we've built over the last few years called Cynomics, which is sort of a collection of a lot of different machine learning methods with some visualization techniques. And the idea is to help accelerate the malware analysis process when you're dealing with malware analysis at scale. Okay. So, all right, deep neural networks. Okay, so I'm not sure how much I need to motivate the need for new malware detection methods, right? It's pretty clear, like, there are lots of systems for detecting malware out there, and yet we still miss a lot of malware, and networks still get compromised all the time. So I think that's a good motivation for additional research on doing malware detection. So actually Last Line came out with a useful study about a year ago on the performance of antivirus sensors in the face of new malware. So it turns out, like, on average, AV sensors miss, like, if you were to randomly pick an AV sensor and give it a new malware sample that hadn't been seen before, it would have about a 40% chance of missing that malware sample and labeling it as benign. So that's enough of a missing 40% of the malware is enough to get a lot of networks compromised, right? And then in the Last Line study, they looked at sort of hardest to detect malware, and they found that it takes AV engines a long time to catch up to like really well crafted malware. So the hope is that a machine learning methods, we can't expect a machine learning based. So the antivirus industry, I think it's hard to know because of intellectual property restrictions. It's hard to know exactly how all the AV engines work. It seems that they're using mostly signature based approaches, right? And the hope is that if we apply machine learning to the problem, we won't be perfect, but we'll be imperfect in different ways, right? So we'll hit some of the malware that the antivirus engines are missing. And so actually I'm just going to skip to the end. So this is a spoiler. I have no shame in saying that. And I'm going to just discuss our results thus far on this project. So what we found is that, so we've actually evaluated our ability to detect new malware. And we get a 60% detection rate on new malware when our false positive rate converges to around 0. So just to explain really quickly, so the neural network has sort of a dial. We can dial up the sensitivity, and we can detect more malware, but get more false positives, right? Or we can dial down the sensitivity, detect less malware, but get fewer false positives, right? And so actually this chart here, this chart here shows, if we sort of dial up the sensitivity so that on our customers' networks we get like 5 false positives a day, right? We can detect like 90% of this new malware, right? So this would be like malware that we've never seen before. So it depends on how much false positives you're willing to tolerate. But so for us, this took lots of like nights and weekends of research, and this was like a good result for us, right? Because it's not out of the box. You cannot achieve these results using machine learning. So I'm going to go into now how we achieve this result, and hopefully I can answer questions if they come up in terms of some of the math behind how we did what we did. Okay, so to begin the exposition of how we approach the problem, I'm just going to start with sort of like our just high level intuitions about what a good solution might capture. So a good malware detector, we think, right, should exploit shared code relationships between old malware and new malware, right? Because most malware was not born in a vacuum, right? Usually new malware samples share code components with older malware samples, or they're just new versions recompiled from an old malware sample. So a good malware. So that's sort of the same intuition behind signatures, right? We should be able a good signature captures something that's fairly invariant about a malware family, right? So that if malware family evolves, right, hopefully the signature is still valid. And it really should be the same. It's really the same problem with machine learning, right? The machine learning system should automatically learn really a vast number of signatures, right? But good signatures that won't change, that won't fail to detect evolutions of a given known malware lineage. So that's like sort of task number one that any good machine learning based malware detection system should be able to handle. And then sort of relatedly, right, we should, a machine learning based malware system should be able to capture sort of new combinations of the components that make up modern malware. Right? So actually here on the right side of the screen is a screenshot of the SpyEye sort of builder interface. Does everybody know what SpyEye is? Has anybody ever heard of it? It's like a popular malware platform. And what it is sort of like so SpyEye is not a malware program. It's, in a way you can think of it as a platform for generating malware programs based on user specifications. And so in this interface, the user can actually like click these checkboxes and decide to like include or exclude various components from malware. They can actually bring up dialogues and include plugins, right, that can be purchased on the black market. So there's all sorts of ways. So if you think about sort of like this sort of combinatorially, right, a clueless script kiddie, right, can generate new malware constantly, right, by just picking new combinations of plugins and options and that kind of, or including new images with them, new payloads and this kind of thing. And so a good malware detector should be able to detect, like, if there's a new binary that includes a component from some old file, maybe that component is an image, or maybe it's some compressed data that's going to be dropped on disk, right? We should be able to detect that, even though we've never seen that binary before, because it shares a component with an older sample. And then also, so if you think about, and this is also a problem for the antivirus sort of systems that are more signature based, the machine learning system should automatically learn what human analysts, learn by applying their own reason, right? It should automatically learn heuristics about sort of what in general constitutes malware, right? So if you look at AV engines, they often deconstruct the Windows binary file format that's called the portable executable format, right? So all Windows programs are wrapped in this sort of file format that has like headers and fields and stuff that describes how much memory should be allocated and when import should come into the file. So basically, like a good machine learning system, right, should decompose the file into these same attributes, and then it should learn from a large amount of data, right, like what suspicious looks like, right. So that's like the third modeling goal that we had in building our system. Okay, so how does that translate into the math behind sort of building a neural network and giving it the right inputs? I don't have sufficient time to talk about all the details here, but at a high level, we're pulling out 4 different types of data from the binaries that we're doing detection on. So one is something I'm going to talk about in more depth in a second, but this idea of contextual byte features. I'm going to talk about it later, but the basic idea is we're using these to try to detect these shared component relationships. And then another is PE import features. So this is just the list of external functions that a binary declares that it imports. I mean, so a lot of times malware will actually obfuscate these, but that in itself can be telling, right? So basically, we pull out all of the external DLL calls that the file is going to make, and we present that to the neural network for training. We pull out printable string features, but in a special way that helps denoise them. I'm not going to go into much depth about that. If people are interested in the details, they can talk to me afterwards. And then we pull out these metadata features like the fields from the PE headers and stuff like that. So those are the 4 types of features that we're pulling out. And the idea with each of the features, in combination, the idea is that we're giving, it's a machine learning model, right? So we're not actually telling it how to detect malware, but the idea is by giving it this data, we're giving it the opportunity to learn, right? We're giving it the opportunity to learn how to detect the components and to sort of craft signatures and learn heuristics and that kind of thing. Okay, so here's the overall, just to give you a big picture, here's the overall architecture of our system. So first we do the feature extraction, right? We extract these 4 different types of features. That takes about 1 to 2 seconds, just to give you a sense of performance. Then we train the neural network. So we're currently in our lab training on about 400,000 files. So we've collected this data from participating customer organizations. So I work for a commercial company that has deployments in large enterprises. So we get a lot of software from them that we use to train the model. And then we subscribe to malware threat intelligence feeds. So we're constantly getting new malware that we train the model on. Then we do something called Bayesian calibration. So the idea is it's out of scope for this talk, but it's a model that sits on top of the neural network and translates sort of neural network output into a probability. And it's sort of cool because like, I mean, most like a lot of security products will give you like a threat score. You know, and the threat score will say, oh, you have, you know, the threat score is red, or it's 90, right? It's not really clear like what that means, right? And so it would be useful if that was an actual probability. And you know, it's useful if it said 90. That really meant in the real world, right, that like 9 out of times it said 90, you were actually looking at malware, right? Achieving that is really hard, right? And so what we built this Bayesian calibration model to try to do that. So that's it. That's the architecture of our system. Okay, so I want to go into a little bit of depth about these contextual byte features, because I think they're probably the most novel sort of aspect of this project, or among the most novel aspects of this project. So here's the basic idea with contextual byte features. We take the file and we take, you know, for each binary, whether it's malicious or benign, right? We take it and we assume basically nothing about the file format, right? And that's useful because malware is basically, you know, a veritable zoo of file. So I mean, malware comes usually packaged as a PE file, and actually what's in scope for us is just to analyze PE files. But within that PE file, it's like a whole zoo of file formats, right? I mean, you find embedded shell scripts, you find, you know, ciphertext, you know, encrypted using custom encryption algorithms. It's a really arbitrary mess of things that goes on in there. So it's useful to not have to, you know, think in advance about what those formats are. That's what we're doing in this case, right? And basically all we're doing is we're counting up every byte that we see in the file, but in the context, in the entropy context in which we observe it. And so if people aren't familiar with entropy, entropy is an information theoretic idea, and it basically just gives you a sense of how random some data set is. So in our case, we look at we pull out these 1024 byte windows. So actually I'll just describe the algorithm and hopefully it'll make sense. So we slide a 1024 byte window over the file, right, over the length of the entire file, advancing at each step 256 bytes. And in each window, we calculate the entropy of that window. So how random that window is. So for example, like if you're looking at compressed data, it's going to have a very high entropy because it's like, if you've ever looked at like a hex dump of compressed data, right? It's almost random in terms of how the bytes are, and there's a good reason for that. But basically, it looks very random, right? And it is very random. Or ciphertext, right, will also be very random. But if you're looking at like natural language text, like a string, it'll be very low entropy, right? Different data types will occur at different entropy levels. And so we count up every byte in terms of like the entropy context in which it appears. And then we get this sort of matrix-like visualization like this of the file, right? And so this is a count. So on the y-axis, you're seeing the entropy of the context in which bytes appeared. And on the x-axis, you're seeing the actual byte values, right? So it's 0 to 256 byte values. And you can see there interesting structures pop out when you visualize the file in this way. So just to motivate this a little bit more, so let's say we take two very different types of data and represent them using this byte entropy method. So here I took like my kernel log on my development system and I compressed it using gzip, and then I visualized it. So hopefully this is unsurprising to you guys, right? That all of the bytes occurred at this high entropy level, right? Because they're compressed. Yeah. Then I took etc services, right, which is just like a standard, you know, file in a Unix system that describes, like, you know, service to port mapping. So that's like a text file, right? And like all the data occurs in like the ASCII range, right, down here, and at a much lower entropy level, right? So the data are much less random, right? So you imagine, you know, I mean, hopefully you're starting to get an intuition that if we showed a machine learning model, you know, different examples like data that look like this or data that look like that, it could start to learn some sort of generalities about, like, you know, in the case of malware versus benign, what sort of images look like malware and what sort of images look like benign. So like let's actually, so I'm going to go through and actually simulate, right, the kind of like component addition and subtraction operation that the malware actually does when it evolves. So here I took the visualization, the byte entropy visualization for bin ls, right, so a binary program on a Unix system. Looks like this, right, and then I just inserted in a random location in the file some compressed data, right, and then here's how it changed, right. Does that make sense? So before in the binary program, we didn't have any high entropy data in bin ls, right? And then because I inserted in some arbitrary position in the file, some compressed data, all of a sudden nothing else changes about the representation except we see the component pop in, right? And of course, like if it did have some compressed data, it would, you know, this would clobber that representation. But still, there would be lots of parts of the representation that would be invariant to that component addition, right? So you can imagine this gives a machine learning system the opportunity to learn that there's some invariant regions of a malicious platform, right? That it can sort of key on, right, in order to distinguish that platform from, say, benign ware. Okay, so I'm gonna give another spoiler, and before even describing the neural network, give you guys some sense of how the neural network sort of interacts with these byte entropy features. So our neural network actually has 2,048 neurons, but it just randomly picks some neurons and look at sort of where they focus on in this image, right? So here we see neuron 1. Like basically, it's a neuron's sort of a neuron's focus corresponds to its brightness in this visualization, basically. So basically, neuron 1 just focuses on data in this entropy band, right? Neuron 2 specializes in data in this entropy band. And then neuron 3 doesn't focus on an entropy band. It seems to focus on sort of vertical byte patterns, which is sort of interesting also, right? And if you visualize the whole neural network, you see that like individual neurons sort of specialize to detect patterns in different parts of the data. Okay, now I'm going to talk about actually building the neural network. Okay, so first, what are neural networks? How many people know a lot about neural networks in the audience? Okay, that's cool. There are some people who do. Okay, so this is going to be like a basic introduction to neural networks. So basically, like if anybody's done like Fourier analysis in the past, neural networks, I think, is a good way of understanding neural networks is sort of like it's by analogy to Fourier analysis. So in Fourier analysis, the idea is you can have an arbitrary complex waveform, right? And it can be decomposed into like simple waveforms that are just like sort of summed up, right? In neural networks, the idea is you have some input data, right? Like the features that I was just showing you guys. Then you have a hidden layer that computes some like nonlinear function on the input data, and then those functions get summed up in these output units. And the result is you can approximate like here a neural network is identified this sort of S-shaped function, right? As separating these red dots from these blue dots. The neural network can really learn arbitrary functions, right? And that's useful. So let's see. I'm actually going to show it. So in the first part of the talk I showed this. I'll show it again, and hopefully it's worthwhile, right? So here's a neural network learning an arbitrary function, right? It's learning how to separate the green dots from the red dots. And so in a high dimensional space, like I talked about in the first part of the talk, right? It can learn. You have to sort of just get into sort of a fantasy way of thinking about this high dimensional space, but basically it identifies a boundary in these high dimensional spaces also, right? So basically what our neural network is doing is like in the case of this image. Each one of these cells, right, represents a dimension, right? And the neural network is learning in this high-dimensional space of all of these byte entropy counts, right? It's learning a boundary around malware, clusters of malware and clusters of benign ware. So then there's this idea of deep. So traditionally neural networks had like 3 layers, right? There was like the input layer, there was a middle layer that computed, these nonlinear functions that got summed up in the output layer. Like in the last 10 years or so, people have started building much more complicated networks called deep neural networks. And this is particularly the case in computer vision. So in computer vision, like deep neural networks have become, they've achieved remarkable results in the last 5 years or so. And it's due to these deep architectures where you stack lots and lots of different layers on top of each other. And so sort of the classic story behind these deep neural networks in computer vision is that you start with the input features like pixels from an image. This first layer sort of specializes in learning how to recognize just like edges in the image, like sort of very basic visual primitives. The next few layers, start learning sort of in the case of a face recognition task, right? Start learning facial features, like literally. And this is not just a story, right? I mean, if you dig into this domain, you'll see this is actually true, right? Like you'll have neurons that specialize in recognizing eyes and ears and noses, right? And then finally, at the most abstract layer, right? You have neurons that actually can do facial recognition tasks. And people have achieved really astounding results in the computer vision field using these they're called deep architectures. Okay, so how do we train neural networks? That would be a lecture unto itself. But there's a very elegant algorithm called backpropagation that basically it has the very nice property that you only have to, in order to sort of do the math to learn how to train the neural network, you only need to do sort of simple calculus on the individual neurons, and then you can use something called the chain rule in calculus to figure out how you should update your neural network on each training cycle. It's out of scope of this talk, but I just wanted to introduce the idea. So here's the neural network architecture that we built. It's a lot less deep than we found that we don't need as much depth as the computer vision people do. We really just need 4 layers, right? So on the first layer, we present the neural network with the features that I described before. The second layer is a hidden layer with 1,024 neurons, we just said we picked that number using trial and error and using a validation data set. Then we have another layer of the same size, and then finally we have a single neuron, and that neuron's job is to say malware versus benign-ware. Okay, that's the architecture we're using. Does anybody know, this was like a meme for a while, does anybody know what this is, or know where this image came from? Yeah. So like there are some researchers like, so this is a visualization of a neuron using the computer vision system that some Google researchers trained. And it's a cat, right? And so the interesting thing is, right, so if you, it's a visualization of the weights of the connection coming into the neuron basically. And the interesting thing about this is, right, a computer vision system learned to recognize cats, right? And the hope is, right, so like in these images that I showed you before, that we're learning to recognize software components, right, through these patterns. I'm not totally sure that's the case, but I do know we're getting good results. I think it's going to take more research to figure out exactly what, in the malware case, right, what deep neural networks learn, right? Okay. So, all right, so I'm going to talk about our evaluation now. Okay, what we found is that there's these deep neural networks. So we evaluated a lot of different machine learning approaches. We tried simple linear models like logistic regression and linear SVMs. We tried SVMs with kernels for the machine learning people out there, and we tried random forests, which for a while we thought were the best possible approach. And then we started down this deep learning path, and that blew out of the water our previous results. And so here are the results. So I'm giving the results in the form of a ROC curve. I'll talk about that in a second, but just sort of the high level bullets are that we can detect about 75% of malware that our system has never seen before, right? So you can think of this as like zero-day malware or malware that that's been newly generated, right? At a 0.01% false positive rate. So that's like 10 to the negative 4 false positive. So it's a very low false positive rate. Then if you relax the false positive rate requirement a little bit, we can detect 95% of the malware at a 1/10% false positive rate. So this is the best we've seen of the published results, but we could be missing something also. So here's a ROC curve that sort of gives more detail about the results. So the idea with the ROC curve is that so this axis is the true positive rate, the y-axis. This axis is the false positive rate. And depending on how you dial sort of the neural network, you can detect more stuff. You can get a higher true positive rate if you allow for a higher false positive rate, right? But if you want a low false positive rate, you have to give up some of your detection accuracy. So this just sort of visually shows what I just described, right? So if you allow for like a 0.001 false positive rate, you can detect most of the malware. But it depends on how you're deploying the system. Okay. So we were worried that our results were too good, and we wanted to make the test harder. So instead of just in the first test, we just randomly picked some data. Trained the neural network, and then used the other data that we didn't pick for training to test the neural network, and we got the results I just showed you. But we were worried that we weren't really capturing our ability to detect evolving malware, right? So then we did a second evaluation where we ordered the malware by compile timestamp. So every portable executable has a compile timestamp, right? Unfortunately, the compile timestamp is not that reliable since the malware author can change it if they want. We just, for the purposes of this test, we assumed that most of the malware didn't do that. We threw out data from like 2025, right? Because unlikely malware came back from the future to attack us. And we just kept malware within like a reasonable range between 2000, year 2000 and present. And we split the malware such that we trained on all the data from 2000 to July 31st, 2014, and then we tested our ability to detect malware that was compiled afterwards, right? Or at least that it tested to be compiled afterwards, and we found that our results got much worse, right? So in this case, right, at a 0.001 false positive rate, we're able to detect about 80% of the malware, which is interesting, right? I mean, it just validates it validates what we all know, right? Which is malware is evolving, and the more time lag you put between your training data and your test data, the worse your classifier is going to do. And this is sort of what I was talking about in the first part of the talk. Okay, so there's those two evaluations, right? And those are sort of in-lab evaluations, and you can do with them what you will. What really matters, right, is when you deploy a system on a customer network, how does it perform, right? So we got these results, right, which is what I introduced. So we've actually been continuously testing our system on customer data. And we have on the order of like 10,000 hosts that we're performing the detection on. And what we're finding, to the best of our ability to evaluate, right, is that we can detect most of the malware with a reasonable false positive rate. So there's a lot left to be done. So this is an ongoing project. There's a lot left to be done in terms of like we want to see how correlated we are in terms of what we miss and what we get with antivirus engines. That's like an important question we need to answer. But we think it's promising work, and I think what I'm hoping that I can convince people of here, right, is that machine learning has become a valid approach for solving the malware. For a long time, it was not a valid approach, and I think that with the newer machine learning technologies that are out there, and the ability to scale, ability to use GPUs, that we're using GPUs to train, right? I mean, we have a bunch of enabling factors that have come together that have enabled at least us, from a commercial point of view, to actually use this technology in a way that's effective. Okay. Okay, let me quickly take questions because I'm going to go into the next case study. Yeah, please. So the question was, do we use GPUs to train the neural network? And yeah, we use GPUs. We use the most expensive Amazon GPU instance. Yeah. So yeah. Any more questions? Yeah, go ahead. Yeah. So the question was, how did we pick the window size in the byte entropy feature representation? So it was trial and error. So I mean, what we found. So there's a trade-off between. Not to spend too much time talking about this, but so if you increase the window size, you get a better estimate of the actual entropy that you're. So I mean, the idea with entropy, right, is there's some underlying distribution that the data you're looking at was sampled from, and to estimate that distribution, you should have a good deal of data, right? Since this is a 256-dimensional distribution we're estimating, because we're looking at individual byte values to estimate the entropy. So if you increase the window size, we get a better estimate of that distribution. But then we have these boundary conditions where when you move from one component to the next, you get some noise in there, you know. So anyways, what we converged on was the window that we picked, 1,024 bytes. And yeah. Last question. Yeah, please. Yeah. How do you deploy it on the endpoint? So the question is, how do you deploy this on the endpoint? So the answer is we don't. So our setup is that we have a cloud kind of solution. So yeah. Okay. I think I'll move on, and hopefully there'll be more time for questions at the end. So the next project I'm going to talk about is actually less mature than what so all of the stuff that I'm describing is in progress. Maybe the last project is the most complete, but the second project is more in progress, so there's going to be less validation, but hopefully you guys will find it interesting and maybe will inspire your own research. So the problem we were interested in engaging here was predicting in advance which malware families were going to be most successful, right? Because malware is at least in the crimeware worlds, right? Malware is a business. And people are interested in predicting business outcomes. I think in the security industry, it may have utility to predict which malware families are about to take off and become sort of celebrity malware, and cause big problems on the internet, right? So just to give some more motivation, right? I mean, so there have been efforts in the security community to disrupt big botnets, right, or to target individual malware families that have been seen as like big pain points, sort of generally across the industry. It would be nice if we could, before those families reach the inflection, or just as they reach an inflection point where they're going to become big problems, we could detect that and intervene early, right? As opposed to waiting until they're all over the news and we have to intervene. That's one motivation for this work. So I think it's a question of whether or not we can predict takeoff early on. And so the approach we took in this project was to look at initially sort of economic models of adoption of adoption of new technologies over time. So if you think about like the adoption of smartphones, for example, you had this initial period where there were early adopters that started to adopt a smartphone, right? Just as perhaps when a new malware platform comes out, there's initial groups of whatever organized crime or criminal actors, right, that begin to adopt it, and then as the technology becomes proven, right, perhaps there's a sort of takeoff, right, where you move from this sort of slow linear growth and you have this sort of accelerating growth, right, and then you're in this sort of takeoff stage, right, and then finally there's some sort of period of taper when the technology gets replaced or goes out of fashion. That was just sort of our big idea when we started the project, and so we investigated whether or not malware actually follows those patterns, right, and so we looked at Zeus. So Zeus has been a big malware, problem on the internet for a while. And we had data around, how much Zeus had been observed on the internet, and we found actually that these sort of S-shaped, this is a logistic function, right? So these sort of S-shaped curves actually fit well with the historical observations of Zeus. So, so in this case, so the x-axis here is our months, month 0. So, in month 0 is when we first observed Zeus on the internet. The y-axis is the number of observations. This is the number of observations not of not of samples, but of unique samples, so unique variants of Zeus. And then we found that we could, when we did a regression analysis, right, we could fit a model, and just visually it looks very similar in terms of its actual, squared error or whatever. It fits very well with the data. So we actually so the results seemed a little suspiciously good, and we were wondering if we had a bad data set. So we actually went and looked at the news and validated whether or not we were detecting whether or not the model actually fit with what people were reporting in the news. And so we found in the news that where we were saying, and where our data showed that Zeus was in this sort of early adoption period was actually when it was first identified by the security community. Right in the middle of its sort of surge, it sort of hit became a big news story and gained media notoriety. And then the creator actually in this sort of slog here, the creator announced that I guess he was retiring from malware authorship. I'm not sure what he's doing now or if he got back into it. So it seems like the analysis is good, right? At least for this family. So this is just to show this, that's not sort of a one-off, right? So here are regressions against 20 different malware families that we looked at. So I'm sorry you can't see the names of the malware families, but so basically we found that we could fit that logistic function to all of these families, and definitely some of them have a sort of more linear growth. The nice thing about logistic function is depending on the parameters, it can become more linear. So that was sort of enough evidence that I think. So at this point, in seeing these results, we felt we had enough evidence to actually start building a predictive model to see if we could predict in this early phase, right? Like when you have the beginning of the exponential growth, right? But like actually signal that okay, this malware family is going into sort of an explosive state. Okay, now I'm going to get into the sort of predictive model. So the basic intuition behind the way we're making the predictions is sort of flows from simple calculus. So if we have this S-shaped curve that describes the growth of a malware family, the first derivative of that function, right, is the rate of change at any given point in that function, right? Basically, just how fast that malware sample is growing at any given point. So actually, this black line gives the first derivative, right? Then there's the second derivative, right, which is the rate of change of the derivative. So that's basically how fast. That answers the question. How fast so that doesn't answer the question how fast is the malware growing. It answers the question how fast is the malware accelerating, right? And that's so our idea is that that's what we're really interested in actually. When the malware first starts to accelerate in terms of growth, that's when we should sound the warning. And actually, if you look at the second derivative, right, it's sort of well, yeah, I'll just leave it at that. Okay, so here are some. So we developed a model to do that. I'm not going to go into all the details because there's more to get through in this talk. But basically we developed a model to estimate what that second derivative was based on sort of noisy observation data from these malware samples. And here are some results from our analysis. So this is again like a visualization of Zeus, the number of variants that we observed over time. But basically we hooked up our model to the data, and we had it look at the data like up to each point. So had it look to the data up to here, up to here, up to here. And where there's this blue circle surrounding the line, our model was saying no, this malware family is not taking off, right? It's in a, it's not an explosive growth state. But as soon as you see these red dots, that's when our model is sounding an alarm and saying this malware family is taking off, right? And it's based on this estimation of the acceleration. So that's like a good example. Here's a bad example where our approach is failing, right? So this family LMIR, which I don't know much about, but we have data for. So here we predicted it was taking off right here, and we were wrong. That was a false positive, right? But then we predicted it was taking off here. We were a little late, right? But that was definitely a true positive. And then we have some false positives over here. We have some parameters on our algorithm that tunes the sensitivity. That controls. We can get less false positives if we're willing to give an alarm late and that kind of thing. But there's definitely. Oh, that's odd. I can yell. I don't know. Testing? No. Wonder if this thing works. Hello? While we wait, does anybody have any questions? I can project if you guys can. Yeah. This model? So we've been training it continuously. So we have a feed of data coming in. So the question was, how often do we have to retrain the malware detection model in order to get a good detection rate? And my answer is that we have new training data coming in all the time. And the way that you train neural networks is there's a sort of an online method for training them. So the answer to that question is continuously. And I think there we go. Okay. Yeah. So the answer is we don't stop training. It's whenever we get new data, we do that. We hold out data for validation. So we can keep track of, we don't train on all of the data, right? We hold out some data to make sure that it's actually trained correctly. Okay. Okay. And we're back. So I'm actually this story is a bit truncated because I would like to have a better evaluation here, but we're working on it. Hopefully we'll have a paper come out at some point. So we evaluated our ability to predict the explosive growth of 20 malware families, and then we just so far we've eyeballed the results, and soon we will actually have charts and graphs that show false positives versus true positives. But I can say on a qualitative level, it seems like a promising approach, and it's interesting that we can do as well as we do just using time series data, right? Just using the number of observations over time. And I think an interesting research question is if we start folding in other data, like what platforms are malware targeting, or just other attributes of the malware, can we make better predictions about what families are going to take off? Okay. All right. So now I'm going to go into the final part of the talk about a project that we've been doing over the last few years. Basically, it's a sort of workbench where the idea is to help accelerate the malware analysis process. So the project's called Cynomics. You guys can get accounts on Cynomics if you want for free on beta.cynomics.org. I'll give you guys a demo, and you'll see the URL in my browser in a few minutes. And so some of if you guys saw my talk 2 years ago, some of the ideas are going to be updated versions of stuff we were working on back then. For everybody who's new, it'll be new, obviously. Okay, so Cynomics has two sort of major capabilities. So one it automatically it does automatic reverse engineering on malware samples. So it does the best job it possibly can to detect like what capabilities a malware sample has. So I talked a little bit about this in the first part of the talk, but it basically uses Stack Overflow as a training source to build up a Bayesian network model that determines what capabilities a sample has. And then the second capability it has is identifying a sort of hidden social network between malware samples. So identifying which samples share code with one another. So I'm going to talk about both of those with more of an emphasis on the reverse engineering. Okay, so here's the premise behind Cynomics' reverse engineering capability. Basically, the idea is that the web holds a wealth of technical data that might be used to train a machine learning model that could reverse engineer malware. And so here's an example of it, right? So here's a post on Stack Overflow. Not sure if you guys, it's probably a little small to read, but so in the title of the post somebody says how to get a screenshot, and using the rest of the text is like using a Windows object in C++. And then people compete, right, on Stack Overflow to give answers to that question. So so here's a code snippet, right, that was given as a response to that question. It turns out, right, that the API calls in that code snippet actually show up, right, when you disassemble. If you disassemble a malware sample and link the function call references to the symbols that they're calling out to, right, you can see, okay, find window and print window are called in sequence, right, in the Stack Overflow document, and then we see those calls in the assembly, right. So, I mean, hopefully this gives some intuition or gives some sense of the promise, right, of training a model on, so we have in our database 6 million threads from Stack Overflow, right. Hopefully it gives you some sense of the promise of training a model on that Stack Overflow data, right, and then detecting the capabilities implemented within a malware sample. So overall, the surprising thing for us, because it seemed like a crazy idea, right, is the approach actually works based on the validation we performed. So we're able to detect capabilities in malware. The big assumption here is the malware is unpacked. If the malware is packed, then obviously we can't do the kind of analysis that we'd like to. So that's like, we just treat that as out of scope, and that's a separate problem. So you need to use a good unpacker if you're gonna use our tool. And definitely there are false positives in what we do, but we found it, like we use it, we use this tool in our lab when we actually have to look at a malware sample, and this has been actually this is a research success story, right? We developed this as a research project. We published it, and now it's part of our commercial product. So that always feels good as somebody who works on crazy ideas, most of which don't go anywhere. Okay, so here are the data sets we use. So we used Stack Overflow. We used We used a site called Ask Ubuntu. We used server faults, right? Basically the whole family of sites run by the company that runs Stack Overflow. So lots and lots of documents from lots and lots of places. Definitely a key to this approach is using a lot of data. It doesn't work well if you don't use a lot of data. And here's sort of the overall approach. So basically, we have a config file. We call this system crowdsourced because it's using crowdsourced data. We have a config file that in which you tell the system what capabilities you're interested in looking for within malware. So if you're interested in looking for SMTP functionality, you tell crowdsource, I'm interested in looking for SMTP, and then here's a search engine query for finding posts that describe SMTP. And so that's actually how we get training data, right? And so we use those queries to retrieve all the posts that match the keywords, and we use those as positive training examples of that capability, and then we use the rest of the posts in our 6 million Q&A thread corpus as negative training examples, and then we train this Bayesian network model. And so like I said, we're using a Bayesian network. It's a certain kind of statistical model, allows you to efficiently reason about a joint probability distribution. If you're interested, I can refer you to more resources after the talk. I'm not going to talk too much about it. But we're using this noisy OR functionality with a Bayesian network, and it turns out that was the best approach that we found after a lot of research. A nice thing about the approach is that it's very interpretable. So we run the tool in a binary, and then we can actually explain to the user, right, like why we think that that the sample that we're looking at implements a certain capability. So here's a case where we ran the tool in a binary. We found that the binary takes screenshots, right? That's what the tool thinks. The whole tool thinks it takes screenshots, and then it actually gives the evidence for the idea that it takes screenshots, right? So it found this call, BIT, right? Maybe we don't know what that call does, right? But actually then we also give it a link to a posting in which taking screenshots is discussed and this API call is mentioned, right? So if you want, you can click on the link, right, and go and follow up and figure out why did the model think that the two things were associated. And so here we have lots of symbol data. So it's also an education, so it's an educational sort of tool, right? So you can also learn more about how API calls are used to implement malicious capabilities. And you can even, the tool also actually will give you a snippet of text, where you can see, okay, bitblit was called, right? Well, so where was bitblit, in the text on the Stack Overflow post, that was used to make that inference. So here are empirical results. So a big, probably half of our effort on this project was just evaluation, because evaluating this tool required that we actually reverse engineer. I think it was something like 1,400 samples or something like that. We had to reverse engineer a lot of malware, right, in order to validate that we were actually making accurate detections. So we reverse engineered this malware. Then we labeled the malware, and then we measured how well in terms of true positives and false positives we could do against 14 different capabilities. In the system we actually deployed, we're detecting 100 and something capabilities, but we haven't validated them all. But we validated 14 just to make sure that the system is working reasonably. So we evaluated these 14. So it takes screenshots, communicates via FTP, communicates via IRC, right, uses SMTP, uses SOX proxies, uploads data, downloads data, grabs webcam, does keylogging, etc. Right? And so some of these we don't do very well on, like in the case of downloads data. We have a lot of false positives and a lot of false negatives. There are other ones that we do really well on. Steals bitcoins turns out to be an easy one to detect for whatever reason. It seems based on given the data that we evaluated on, we do perfectly. We detect all of the Bitcoin mining malware. Turns out that's a thing. FYI. Malware can mine bitcoins on your machine. So okay, and then in terms of runtime, it's very fast. It takes a while to train the model, but to actually do the inference on the binary takes less than a second, right? So another thing that you can do with a tool like this is do demographic analysis over a lot of malware, right? So if you have a database like we have in our lab, 2 million malware samples, you can run it over that whole corpus in a couple days, assuming you have a big machine that you can parallelize over. And then you can look at high level trends, right, in terms of what's malware doing, in terms of the whole malware landscape, right? Are we seeing a rise in Bitcoin mining malware, right? Those are the kinds of analyses you can do when you have this automated capability. Okay, so another component of the Cynomic system was the shared code analysis that I talked about a bit earlier. And so we did a lot of different kinds of shared code analysis. Because I talked about that in the first part of the talk, I'm not going to spend too much time now talking about it, but just suffice it to say, right, we spent time looking at shared instruction sequences between malware samples, shared strings, shared dynamic behavior, and then we looked at locality sensitive hashing algorithms for efficiently computing shared code networks over very large corpora of malware, and that's all part of this Cynomic system as well. And that's the dynamic piece that I talked about in the first part of the talk as well. So I only have a few more minutes, I think, actually 5 more minutes. Okay, so now I have the choice of giving a demo or taking questions. Demo? Okay. Okay, so here, is that working? Great. Let's try this again. Oh no. Okay, well, my hand may be forced here. Oh, that's unfortunate. This was all tested earlier and it works. So let me try this. Okay. Okay, no idea why that worked. Okay, so here's sort of like the top level view of our system, right? So the basic idea, we have a bunch of malware in the system, and we're visualizing, like, this is sort of a fun visualization that you see when you first log into the system, right? So this is, we have this grid on which malware that's close together winds up in the same bin in the grid, and we have these spikes, and they're high in proportion to how many malware samples are in the bin. Bins that are close together contain malware samples that share code, right? And so what you're seeing here is that there are a few clusters of malware that really dominate the malware we have loaded into the system right now. So you can go in, and then you can go and have a look at the malware in the system. So I'm going to bring up, so you can do, so right off the bat, right, you just see a list of the malware that you sort of loaded in. So if you're an organization that does malware analysis, you know, this is a, you know, first and foremost, this can just be a repository for your malware. But you know, if you want to zoom into particular data sets, you can do that. If you want to look for, you know, malware that has certain capabilities, you can do that. Like, you know, all the malware that grabs keystrokes or whatever. And this is all based on the crowdsourced capability recognition technology I was describing. And then we can drill into individual malware samples and get more information about their attributes. So here's sort of like a Facebook profile for a malware sample, right? So this is a sample. We don't know what it's, you know, we don't have a better name for it than it's SHA-1 hash, right? But we can see this is its local neighborhoods, right? So it's part of a big cluster, right? So if you're going to analyze this sample, you probably want to analyze it like in conjunction with these other samples in the cluster, as opposed to all by itself. If you have any notes about those other samples in the cluster, right, those notes would show up. In this case we don't, but those notes would show up here, so you could sort of inherit your previous analyses on similar samples in the case of this new sample. And then if you want to drill in and look at like the crowdsourced detected capabilities, right, you can see, okay, compresses data, here's the evidence for why it compresses data. It has all these, it's pretty obvious, right? It has all these symbols that have to do with compression, has a GUI, right? Why do we think it has a GUI? Because it has like these functions like get clipbox, and it turns out that in Stack Overflow discussions of GUI programming, that shows up there, right? We can zoom in and compare to these other samples. Because I only have a few minutes, I'm going to quickly show one more aspect of this system. So we also have this network view, right? So I'm going to bring up the Putter, the CrowdStrike discovered Putter Panda data sets, right, from the Chinese, you know, advanced persistent threat actor. So here I've brought up those malware samples, right, and I can see that, you know, so we successfully identified Putter Panda as a cluster because all of these malware samples, right, and we've got like, I don't know, 10 of them or so, they're all interconnected. That means that our shared code analysis, you know, detected the fact that they're part of the same family. If I click on them, right, I can see their capability, you know, their automatically detected capabilities come up, like they use cryptography, and they also use public key infrastructure, right? Okay, so I'm gonna cut it short there, so we can at least take a few questions, and then people can come up and talk afterwards if they're interested. So, any questions? Yeah. Yeah, so the question is how did we get the Stack Overflow posts? So those are actually licensed under Creative Commons, and they're like conveniently packaged up so anybody can download them and use them for research. Yeah. Yeah, please. Yes, you can. Yeah. Yeah, you go to the site, we'll give you an account, you can upload malware and evaluate it. Okay, I think we'll wrap up. I mean, we're past our time, so feel free to come talk to me afterwards if you're interested in talking more. So, thanks.